So back in AP Physics 1, when we talked about electric circuits, we regularly used this concept of voltage. And we talked a little bit about where this concept came from, but we're now going to delve into much more detail on what voltage really is. And that means we need to talk about a new concept known as electric potential. So let's just go back to a situation we've really talked about in many different contexts now. We have a really big charge here, some sort of source charge, and it is going to physically alter the space around it due to the fact that it has charge. And it does that by creating what is known as an electric field. This electric field spreads out into all space, even if there's nothing else around it, it is still there. Now, that means if we place another charge in this field, this charge is going to experience an electric force. Now, that electric force may be towards the source charge, it might be away from it, it just depends on the signs of the respective charges. Additionally, if we want to take that a step further, we could say that the amount of energy that we needed to place this charge here, so in other words, the work we had to do to put that charge at that point, well, that is going to be stored as electric potential energy in the electric field of this system. And now that we've kind of reviewed all of this, how we connected electric field and electric forces is going to be very, very similar to how we connect electric potential and electric potential energy. So, just to make sure we're all on the same page, I have a big source charge Q, a tiny little charge, little q. They're a distance r apart. The electric force that little q is going to experience, really both charges are going to experience, is equal to its charge times the electric field. And the electric potential energy of the system is just K times the two charges over R. Now, let's say, though, that we moved to a different point in space and we put in a new charge with a different magnitude, but it's the same distance from this point charge. So let's say something like this. So I put now this charge has double the original little charge. So if I do that, well, I would say, okay, well, that means that there is twice the electric force, right? Because they're the same distance apart, the big charge and this little charge. But since this little charge has twice the charge, you're going to have twice the force between them. Well, if that's the case, the amount of energy it would take me to do work on the system and put it there, well, that's going to be twice as big. I'm going to have to do twice the work, we're going to store twice the energy, and that would be used in this equation here, where instead of having low q, I'd have 2q. And let's say we did something similar again. Let's say instead of 2q, we had an even bigger charge, and this charge was 5 times the original little charge q, and we also placed it at some distance r away from the big Q. Well, that's going to take, it's going to experience 5 times the amount of force, and we're going to have 5 times the work, 5 times the electric potential energy in this system, kq times 5 little q over r. But what we notice is just like if I look for all of these, if I have double the force, that's because I have double the charge, but the same electric field. Here I had same electric field, and here I had 5 times the force, 5 times the charge, but the same electric field. Well, is there some way I could kind of apply this to the electric potential energies as well? And there is, because if we look, we see that at some distance r at all of these points from this source charge, we call the source charge the one that's creating the electric field, Q, we see that all of these are really just E, the electric potential energy, is equal to the charge that we've placed in this field times some constant, because that constant is kq of the big charge over r, and well, that's constant in all these situations. They're all the same distance, all the same charge. Coulomb's constant is the same. So instead of being, q times the electric field gives me the force, I have q times some constant gives me the electric potential energy. And what could we call this constant? Well, we could call it, let's abbreviate it with a capital V. So I'm going to go into, for instance, this equation. Let's go on the first one. I'm going to get rid of this. I'm just going to say Q times V. That gives me the electric potential energy. On this next one, I'm going to cross this out. I'm going to call that V again. So V times 2Q will give me twice the electric potential energy. And if I go to this bottom one, I'm going to get rid of all that, and I'm going to say it's just times Q. Well, V times 5Q will give me 5 times the electric potential energy. And this is all perfectly acceptable. So essentially what I've said is that every point in space, a certain distance away from that charge, there is some constant that quantifies basically how much energy per charge we could have. So if I want to know the total energy, I just multiply it by the amount of charge. And this is something known as the electric potential. So the electric potential is abbreviated with a capital V. And this is really the potential to create electric potential energy at some specific point inside an electric field. So think about an electric field for a second. That when you have an electric field, what that is telling you is at every point in space, the potential to create electric forces if you were to place an electric charge there. It's the same concept here, that I instead have the potential to create electric potential energy if I place some charge inside the field. Now, something I want to be real clear on, potential is not potential energy. It is potential. Those are two separate concepts. We need to be real careful there. And what this is really telling us, like I said, is how the electric field will gain electric energy per unit charge we place in the field. So if I place, 1 coulomb, you'd multiply that by this electric potential, and they'd get some sort of electric potential energy. If it was 2 coulombs placed in the field, you multiply it by this potential, get some amount of electric potential energy, etc. So the equation for let's go ahead and say first off, the relationship between the electric potential energy and electric potential is the electric potential energy in joules is equal to Q. This is the charge placed in the field, not the charge making the field. This is the tiny charge placed in the field. And multiplied by the electric potential, which is the energy per unit charge. So that would be joules per coulomb, just like electric field is newtons per coulomb. Now, the thing is, though, is that we actually have a name for this unit. That joules per coulomb is way more common than newtons per coulomb, and so we have basically now called this the volt. 1 volt is 1 joule per coulomb. But it's the same thing, like for instance, for electric fields, you have newtons per coulomb. We just don't have a name for that. We don't call it the NOLT, it's just newtons per coulomb. Here we have one specifically, that joule per coulomb is the volt, which we abbreviate with a capital V, which as you can see is real annoying, because that means the variable V and the unit V are the same. So you have to be super careful that you do not get those confused. And that's annoying, I know. There's just no way around it. Additionally, as we said, the electric potential is therefore the electric potential energy per unit charge. Exact same equation, just reformatted. So let's look at an example. Let's say we have a +4 microcoulomb charge. It's placed in the electric field of some large positive charge. We don't know what that charge is. And it results in the system gaining 0.012 joules of electric potential energy. So when we place that little charge there, this much electric potential energy is created. And the question is therefore, what is the electric potential of the source charge at this location, the location of the +4 microcoulomb charge, and what is the electric potential energy of the system if we basically, instead of having a +4 microcoulomb, we had a +8 microcoulomb charge located the same distance away. If you had a +2 nanocoulomb charge, a -2 millicoulomb charge. Let's go ahead and see how we would do that. So I have the system once again, and I go ahead and look at the UE is equal to Q times V. So the electric potential energy is equal to the charge placed in the field times the electric potential from the source charge. So I go ahead and rearrange that. So I get V is equal to UE over Q, and I just plug in my numbers. That 0.012 joules divided by 4 times 10 to the -6 coulombs gives me an electric potential of 3,000 volts. So what that tells me is that at any point that is this distance away from the point charge will have an electric potential of 3,000 volts. So if I have these new charges all located the exact same distance away, well, that tells me the electric potential at all these is 3,000 volts. And now if I have 3,000 volts, which is 3,000 joules per coulomb, and I have the amount of coulombs placed in the field, I can multiply them together to get the electric potential energy created by placing any of these charges in the field. So basically I've created a shortcut. Rather than having to do the whole calculation every time, I can just multiply the charge by the potential and get the electric potential energy. So let's go ahead and do that. So I'm going to have my electric potential energy equation, and I just multiply the values together, and I get that, for this 8 microcoulomb, it's going to be 0.024 joules, which makes sense. You have double the charge, you should have double the energy. If I have plus 2 nanocoulomb, it'll be 6 times 10 to the minus 6 joules. If I have minus 2 millicoulombs, I'll have negative 6 joules. Now notice it's negative, so we get a negative electric potential. And so something that we can say about this is that at any point, that is this distance r away from the big charge, we could connect all those points together in like a really big circle, and we would call this an equipotential line. So equipotential meaning it has the same potential, electric potential at every point on that line. And we would specifically say it's the 3000 volt equipotential line. Now let's say though that we went closer to that source charge. Well, if we go closer, well, we know that the electric potential energy would go up, so that tells us that the electric potential energy per unit charge, or the electric potential, would also go up. So if I move in closer, I'm going to get a bigger equipotential, and if I move even closer, the equipotential is going to go even higher. I'm going to get an even more positive number. In the previous video, we analyzed how the electric potential energy of a system of charges changes as we change the distance between them. So let's now do something similar, looking at, well, how does the electric potential of a charge, so from the singular charge, change as we move closer to and further away from it? Let's start off by looking at the situation on the right. So remember, I have positive and negative. This is the electric potential in joules per coulomb, which is the same thing as a volt, and the distance is in meters. And we get a positive electric potential if we have a positive source charge. So in other words, if I have a positive charge creating the electric field, it will create positive electric potentials. Additionally, this is an inverse relationship that V is proportional to 1 over R. And we'll see a little more specifics about why that is in just a second. Similarly, if I have a negative charge, if I have a negative source charge creating an electric field, it creates negative electric potentials. And additionally, once again, it is inversely proportional. So let's come up with a way to calculate the electric potential from some charge in a slightly different format. So we already know that the electric potential energy is equal to the charge times this potential, and that therefore, if we just rearrange that the potential is equal to the electric potential energy over the charge. Well, I could just plug in my equation for electric potential energy, where I've used big Q and little q instead of Q1 and Q2, where we're going to say big Q is the charge creating the field, and little q is the charge placed in the field. But if I do that, we get Q over R. This Q and that Q are going to cancel, so we're going to be left with just KQ over R. And this is, in fact, the equation, or another equation, for electric potential. Specifically, this is electric potential for a point charge. That doesn't mean it's not like a plate of charge or anything like that. It's just a single isolated charge. But that electric potential of that point charge, which is in joules per coulomb or volts, is simply equal to Coulomb's constant times the source charge, that is the charge generating the field, and over the distance from that point charge. Now, real careful, as I noted here, do not use just like electric potential energy, don't use an absolute value here. Because what's going to happen is if I have a positive source charge, well, that would be a positive over a positive, you're going to get a positive electric potential. Makes sense. If we use a negative point charge, you're going to get a positive times a negative over a positive. That will generate a negative electric potential. So it works out. And just like with electric potential energy, there's a couple things we just need to keep in mind. That essentially, we've defined V equals 0. So when there is no electric potential as being an infinite distance away from the charge. So essentially at the point where the electric field does not affect something else. But additionally, to calculate delta V, remember we would do KQ over R minus KQ over R naught, where R is the final distance, R naught is the initial distance, and therefore remember, do not combine those denominators. We would instead just do KQ of 1 over R minus 1 over R naught. So just be very careful of that. But this delta V is a very important thing that is often called electric potential difference, but you know it as a much more popular term, voltage. Voltage is a very important concept, so let's try to conceptually think through what it is before we formally define it. So let's say we have two uncharged metal plates here. This is really just an uncharged capacitor. There's no excess charges on them. So the electric field between these plates is going to be zero. There's no electric field there. So if I place a charge in this, zero electric field at point A, and then I move it to point B, well, there's no electric force stopping me from doing that. And that means there's going to be no work required from me. We can just do it without expending any energy. Well, if there's no work, there's no change in electric potential energy. And if there's no change in electric potential energy, none of that is stored. Well, then, if we remember that UE is Q times V, well, then V is U over Q. So I could say instead that this delta V, which we're going to call voltage, is equal to delta UE over Q. Well, that's also going to be zero. So in this particular situation, there is no voltage between points A and B. No voltage exists there. But now let's say we charge the plates up oppositely. So we have a bunch of positive charges on one plate, a bunch of negative charges on the other plate. This is a charged capacitor. And if we look, there's definitely an electric field between these plates, and it would point to the left because it always goes from positive to negative, the direction that a positive charge would go. And let's go ahead and say that I put this charge at the exact same location, A, in this electric field, and then I move it to B. Well, when I put the charge in here, it's definitely going to experience an electric force from these plates, specifically pushing it to the left from the electric field. So to push it the other way, I'm having to do work. I'm literally pushing it towards the positive charges, doing positive work, which is storing and creating positive electric potential energy. But that means I also have created a positive electric potential difference between these 2 points, or in other words, we could call this a voltage. A voltage exists between points A and B because it all really comes down to this, that to have a voltage, you really just need to separate charges, positives away from negatives. So a voltage or electric potential difference, which we abbreviate delta V. Now we have to be real careful. It is often called a potential difference, often called a voltage, electric potential difference. They all mean the exact same thing. So, real simply, this is the difference in electric potential between 2 points in space. Typically, though, it's a result of separating positive and negative charges. If we separate those, we create this potential difference, aka a voltage. So what are some examples of this? Well, batteries. Batteries have separated charges. Capacitors, when they're charged. We talked about this in our weekly deep dive. So storm clouds. Storm clouds have a separation of charge. The Van de Graaff generator, which we will look at more later, has a separation in charge. All of these create voltages. So to just quickly get a nice formal definition, that delta V is going to equal to delta UE over Q, or similarly, if we rearrange it, delta UE is equal to Q times delta V. This is a really important relationship we really want to make sure we have down. And additionally, one thing we want to add is that if you have a positive voltage, a positive delta V, that means you are moving toward a positive charge or away from a negative charge. If we go towards a positive or away from a negative, we're going to have a positive voltage. If we are doing the opposite, if we go toward a negative or away from a positive, we will have a negative electric potential difference or a negative voltage. But you might be thinking, why do we hear about voltages so much? Like, why don't we talk really that much about electric fields or electric potentials? Why is voltage the term you hear everywhere when you're talking about anything like electronic or electric or something like that? And there's a real big reason for that, which is to go back for a second. Remember that electric fields accelerate charges. If we had some electric field like between these 2 charged plates, if we were to put a positive or a negative charge there, they would immediately accelerate due to the electric forces that they experience from that electric field. But there's an issue with that, which is it's real hard to directly detect electric fields. We can't measure them directly very well. Instead, we usually just calculate them from the results that we see. So, we can instead think about the fact that a voltage that exists between these 2 plates indicates the presence of an electric field. That if you have an electric field between 2 points, you have to have an electric potential difference or a voltage between 2 points. And this voltage also indicates the ability to accelerate charge. If you have a delta V, charges will accelerate. And what's most useful about it is we can measure this. We can measure voltages using a voltmeter. And because of that, because we can directly measure it, it is way, way more common to see because we can get those measurements directly without having to get them through calculations. So let's go through a couple of practice problems. These are not going to take very long. So let's say we have some big source charge. Well, it's not that big, but it's plus 4 microcoulombs. And we want to know what is the voltage that occurs when we move from point X, which is 0.3 meters away, to point Y, 0.1 meters. Go ahead and pause the video. Give this a shot. So if we want to know the voltage between these 2 points in space, that means we need to know the difference in electric potential between point X and point Y. So I'm just going to use KQ 1 over R minus 1 over R naught. And I'm going to stick in my numbers where I have K is 9 times 10 to the 9th, newtons times meters squared per coulomb squared. The charge, remember, micro is minus 6, so that's 4 times 10 to the minus 6 coulombs. Now remember to keep your numbers straight. We go from point X to point Y. So point X is 0.3 meters, point Y is 0.1 meters. We stick those in. And you get a potential difference, or a voltage, between X and Y of 240,000 volts. Well, now that we know that the voltage between point X and point Z, for instance, was plus 240,000 volts, we can quickly calculate how much work is required to move an electron from point X to point Y. And notice we have a couple of different paths here. We have path 1 and we have path 2. So if I placed an electron on point 1 and then moved it to point X and moved it to Y, what would the work be? And then if I did on path 2, what would the work be? Well, for the first situation, I would say, well, the work is equal to delta UE, which is equal to Q times delta V, the charge times the voltage. And if I look at here, well, the charge would be the charge of an electron, the charge we place in a field. Remember, this is little q, it's the charge you place in a field, times the voltage, 240,000 volts. I multiply those together, and we get that the electron would require negative 3.84 times 10 to the negative 14 joules of work to move between X and Y. Quick note, why is this negative? It's negative because this would happen spontaneously. That an electron will naturally move from X to Y because it wants to get closer to that positive charge. So we're actually using energy to stop it and to keep it in that position to prevent it from going to the positive charge. Well, what happens if we took the electron and we moved it along path 2? Well, there's no difference. It is the same work no matter what the path you take is. The path does not matter, because the force you are working against is the electric force, which is a conservative force. What I mean by that is if I move, directly between the two, well, that's a nice, quick, easy way to do it. But if I go the other way, you're going to have fluctuations in the kinetic energy and the electric potential energy, and it's going to all happen in such a way that you always end up with the same result. The path you took to get there does not matter, just the difference between the 2 points. So lastly, what were our takeaways on electric potential and by that voltage? Well, one, can we conceptually differentiate and connect electric potential energy and electric potential? They are not the same thing, but they are very, very deeply related because the electric potential is simply the electric potential energy per unit charge placed at some point in an electric field. Can we calculate the electric potential of a point charge at some point in space using V is equal to K big Q over R? Can we calculate the voltages between 2 points in space and then connect that delta V to work by multiplying that voltage by some amount of charge that we're moving? And can we analyze drawings of equipotential lines? We haven't done a whole lot of that yet. We're going to do way more of it in class.